This unit is called uh, kinetics. If you can try to relate that to kinetic energy, then it's basically going to be about how the movement of particles really affect reactions. So you may have wondered, probably, that why does it take a second for fireworks, but when something is rusting, how come it happens over a very long period of time? What makes baking cookies or whatever take, okay, I don't remember anymore how long it used to take to bake cookies. It's been a while, 30 minutes, 20 minutes, I don't know. So how is it that some things are taking so long, but some things are happening instantly? For example, the spark of electricity, how does it blow up the entire house in an instant again? So all of this basically depends on the collision theory. So why are some reactions faster than others? What makes them faster than others? So each and every reaction in the entire world that's happening around us has a certain demand in order for it to happen. This is why you would require to introduce, say, spark or actual, light something on fire in order for a reaction to happen. But in other cases, just say exposing it to air, like rusting, that would make a reaction happen. So that minimum amount of energy that's required for that reaction to happen, it's different for every reaction, and it's also called activation energy. And for that to happen, the particles must successfully collide with each other. And if there's a lot of successful collisions, what I'm trying to say over here is that not every collision is successful. But the ones that are successful are the ones that will make the reactants turn into products. So how can you make those collisions successful in order for your reaction to happen? We're going to be learning about that. Okay. Also, reactions do not proceed at a steady rate. They start off at a certain speed, then they get slower and slower until they stop. As a reaction progresses, the concentration of reactants decreases. Think of this as you trying to bake bread in the kitchen, okay? So initially, if you have, say, 5 kilograms of dough, and then you have the required amounts of yeast and whatever, gradually, the amount of bread that you're trying to produce, it was a zero. You had no breads in the beginning of you entering the kitchen, but gradually you are getting more bread, you are producing more bread, and at the same time, you are reducing the dough that you have. So try to connect that to chemistry, that the concentration of your products, which is your bread in this case, that is increasing, and the concentration of your reactants, the dough in this case, is reducing. This means that, let's say if someone walked up in the kitchen and you were done halfway, you were done baking with at least half of the dough, they're not going to be producing as many breads as you were initially. So basically, as the concentration of your reactants decreases, it also decreases the frequency of collisions between particles. And for that very reason, the reaction slows down. So if initially you had a lot of reactants, let's look at the picture over here. So at 0%, you have your two reactants, and then gradually notice how when the reactants are turning into products, your reactants over here, your reactant concentration, which is the blue and the red ones, it was 3 before, now it's a 2. Eventually it's going down, and the concentration of your reactants is now a 0, and you have all of your reactants turned into products. So this is a connection that you have to try to make. Now let's look at how it appears on graphs. Chemical reactions involve the conversion of reactants. You guys know that. So you will either be given a graph like this, or you'd be given a table like this. Both of them are going to mean the same thing. So this picture right here is also the same thing as the previous diagram. It's just that it doesn't look as cute as it did on the previous slide. So notice how you have all of your reactants here, and as time is increasing, which I could write as delta T, change in time. Delta means change. As the time is changing, I'm getting more concentration of my products gradually. And notice how my reactants, which are the black ones over here, their concentration is decreasing. On a graph, let's look at what this looks like. So for A molecules, the A is my reactant and the B is my product. So how can I tell from a graph who is my reactant and who is my product? So I can notice that when the time was a 0, when time started, I had 40 molecules of A, and I had 0 molecules of B. Now remember that it's not necessary that they are going to use number of molecules every time. They can give you concentration. For time, they can also, it can change, but the gist would remain the same, that you would notice that your reactants are always going to be going down because they are being consumed and and your products are going to be rising. Now let's look at how you're going to be calculating this, because you will be looking at the graphs and putting in the values into your formula. Remember, there are about two to four things in AP Chem that you'd be utilizing the entire time. We are done understanding the importance of converting to moles, whatever you're given, whether it's a gas, whether it's concentration, you always have to convert to moles. It makes things easier. So the second thing that we have to learn is how to use a reaction, with stoich and figure out the concentration. So the formula to calculate average rate is change in your reactant concentration. So a square bracket in chemistry means concentration. So the change in reactant concentration per unit time. And for your product is again the same, the change in concentration for your product per unit time. The only difference between both of these calculations for average rate is that for the reactant, because it's being used up, we use a minus in the formula. Okay, now let's look at a reaction over here. So the second thing that I reminded you guys about remembering always in AP Chemistry, the second thing is utilizing stoich, right? So you have nitrogen reacting with hydrogen in order to produce ammonia, okay? So if the rate of disappearance of nitrogen is 0.025 molar per second, what is the rate of disappearance of hydrogen and the rate of appearance of ammonia? So we use disappearance for both of these guys because they're the reactants, they're obviously disappearing, and we use the word appearance for your product over here. So what I want you guys to observe is the stoich, the ratio over here. So every time I use 1 mole of nitrogen, I'm using 3 moles of hydrogen, and I'm producing 2 moles of nitrogen. So let's look at the graph over here also, because you may have to interpret it from a graph. So I can see that as my ammonia concentration is increasing, I can see that my hydrogen and nitrogen are being used up, but my hydrogen is being used up more than the nitrogen. I can tell this from the from the dip in the graph, in the curve over here, okay? So let's see, so if it's 0.25 molar per second for nitrogen, how much would it be for hydrogen? I just picked up my conversion factor from the main reaction, and this is what I get for hydrogen. Okay, and then for ammonia, again, I'm going to be using my conversion factor from the reactant, and this is what I get. For MCQs, most of the times you will be getting things that you can, just mentally do the math with. Okay, now let's look at how it could appear as a graph. I'm sorry, as a data table. So here they've given you a reaction. Okay, it's called you don't have to know what it's called, but anyway, it's sulfuryl chloride. So calculate the average reaction rate over the whole reaction. Now, the average rate for my reactant, notice how I am using a minus here per unit time. So for this, for the change in concentration or for any kind of change, we always subtract the final from the initial. Okay, now whether you're doing it for time or concentration or anything at all, this is how we actually look at the change in anything. We compare the final and the initial. So it's always the final minus initial. So for my change in concentration, I took my final, which is 0.060, and I subtracted that from 0.200. And I get a minus 0.140 moles per liter. I didn't have to think of the units, they were just right over here. And the time that took for this change to happen is 600 seconds. Average rate, because I had a minus 0.140 and my formula has a minus in there, I did all the math, and this is what I get. Now, it's just very simple for me to not do any further math in order to figure out the average rate for the other guys in the reaction, because I can see that they are all a 1-to-1 ratio for all of them. So I didn't have to do any math for this specific reaction, and I would have known that, oh, okay, it's going to be the same for all of the other participating members. However, it's not always going to be like that. So for that, you're going to be using the stoic that we did, the conversion factor that we did on the previous slide. Just the main thing to remember here is that for the average rate of your reactants, there's always going to be a minus, and it's a normal delta concentration versus time. Okay, one of the other things that you have to remember for this is there are not many elements on the periodic table that help us recognize them only on the basis of color. So there could be on the basis of smell and a lot of other things, but there are not many that, really help us identify by just visually looking at them. So here's a question that tells us that in an aqueous solution, molecular bromine reacts with formic acid. So what you have to always remember about bromine is that it has a reddish brown kind of color, and everybody else is colorless. This is the only reason why they would be using bromine in a question like this. So as the reaction progresses, obviously, because your bromine is a reactant over here, the color is gonna keep getting lighter. Now, think of this the other way around, that if bromine was your product, if it was being produced in a reaction, the color of your reaction would be going darker. On the basis of that, the question has further introduced one of the concepts that you already know about concentration, that whenever we want to look at the concentration of a chemical, we use spectrometers, right? Which helps us, which tells us the concentration of things. So what you have to do is that you have to calculate the average rate of reaction on the basis of this table over here. Over the first 250 seconds relative to bromine. Now, because it's your reactant, you are using the minus formula, okay? And you picked up your, because they specifically have asked you to only look into the first 250 seconds, I am going to be using these values. So I took my final concentration, which is a 0.00500, and I subtracted my initial, which is 0.0120 over 250, because they have asked us to do it in 250, and this is what I get. Calculate the average reaction over first 250 seconds relative to bromine ion. Now the bromine ion is my product, okay? Notice that it is different from your initial from bromine itself, and also the ratio is different. So every time I have two bromine ions appearing, every time I have two bromines appearing, I am using only one bromine in my reactant. So that's half of my bromine. So in order to bring our two different rates together, okay, I did it for bromine, and I used my stoich for this one, okay? I had my data for bromine, and I used that in order to calculate. I did the same steps that we did over here in order to figure it out for the bromine ion, okay? Okay, and then we have another reaction over here. I would want you guys to try this on your own. Okay, so you have all your concentrations, okay? When you're gonna be calculating for these guys, remember there's gonna be a minus. Okay, so, okay, let's go here. So what are the things that can affect a reaction? Okay, so you have temperature. If you provide obviously higher average kinetic energy to the particles, that means they're going to be moving more, so there's higher chances of successful collisions. Molecular orientation. Now this may be a new one for you. Notice how we have two molecules here colliding with one another. And because they're not colliding in the right way, now if it's shown to you like simply drawn, then you would know that, you know, in order for a molecule to really react with one another, then especially if it's a polar molecule, then that opposites should be reacting, right? So if it's a wrong orientation, or if there's insufficient energy, there's not going to be a reaction happening. Let's look at the concentration. Obviously, if you have more concentrated reactants, you're going to be producing more product. This also aligns with what we just learned about concentration, that as the concentration decreases over time, we start producing less and less products, right? So more concentration of your reactants means there's guarantee that you'd be producing more products. And then we have pressure, again, because when you increase the pressure, you force the particles to come closer to one another. This obviously increases the chances. And then we have surface area. Now, surface area, it was kind of a complicated concept for me when I was in middle school, when I used to be a middle schooler, that's what I mean. It never really 100% made sense to me until I was like a little older. So surface area basically means, think of how when you add a block of sugar, you guys probably have blocks of sugar at home instead of granulated sugar, right? So blocks of sugar take longer to dissolve in tea and coffee versus the powdered one. This is because when you add a block of sugar to whatever, the tea or the coffee is only able to absorb it from the outer layer. It's not able to penetrate in it. It's going to take a bit. But when you add powdered sugar, because the particles are are more in number and all of their sides are exposed, the T has more surface area, right? Like right now, it can only be working on the outside. Now it can go on the inside. It has access to the insides also. So that's why increased surface area is going to give the chance, it's going to give the reactants the chance to interact more with each other. So that increases the chances of successful collisions. Okay. And then we have reactant state of matter. It's interesting, or maybe it's just common sense, right? That if you have something as we're gonna come across a few questions where this is gonna make more sense. Okay, any reaction involving a solid can only take place at the surface of the solid. If you have something in a liquid state, it's going to increase the chance of your reactions. And then we have catalysts. So this is probably, yeah, I'm sure this is the first time we're hearing about catalysts. So a normal definition for catalysts is that they take part in a reaction without becoming a product. So they enter a reaction, they make a reaction happen faster, and then they just leave and they don't become part of the products. How do they do this? So think of a reaction that has a particular demand, okay? And because we want successful collisions, the normal reactants are not able to cause that successful collisions. What if one of the reactants is someone like hydrogen fluoride? Because fluoride is the most electronegative element on the periodic table. It's not just going to break bonds with hydrogen and then react with the other reactant, right? It's gonna take up a lot of energy for us or for the other reactant, the participating reactant, to convince fluoride to leave hydrogen and react with it, right? So it's not just going to happen very easily. We're going to have to get some catalyst intervene. It's going to have to break the bond between hydrogen and fluoride, make it available to the other reactant, and just leave. This is what happens. It basically reduces the activation energy for the reaction to happen by mostly temporarily bonding with the reactant molecules. We'll get into the details of this, not really details of this, but how do we cross them out or cancel them out when we're combining two reactions. Okay. Okay, the very common catalysts are in our own bodies, which are called enzymes. What they do is that they break down starch so that the reactions can happen, but they don't become part, the enzymes don't become part of the products. Lactase, for example, is an enzyme in the human body. It's basically a catalyst that breaks lactose into simpler structures like glucose. Okay, all right. And then molarity, obviously, if you have high molarity, it's going to have more reactants available. Okay, so this is an interesting question. I have written the answer to it. Okay. I want you guys to figure this out. I believe this is a, what do you call it? A bulb question. So which graph represents the changes in concentration of oxygen and why? So let's look at the reaction. You have two nitrogen monoxides reacting with one oxygen, and it's producing you two nitrogen dioxides. Okay. So this is your reactant. Notice how the concentration is going down, okay? And for oxygen, they're asking you what would be the right graph that is representing oxygen. So I can tell that, of course, oxygen is being consumed, but it's half of nitrogen monoxide. okay? And when I compare both of these graphs, I know that it can't be a linear line, right? Like they're showing that it barely went from 15 to 14.9, that's it. So it's definitely not graph 2. It is graph 1, but 2 of my options are giving me graph 1. Graph 1, because the rate of oxygen consumption is half the rate at which nitrogen monoxide is consumed. 2 molecules of nitrogen monoxide react for each molecule of oxygen. So what I can see is that this is going from 30 to this is going from 26 to 19. Here I can notice that it's going from 15 to 10. My second option is that because oxygen molecules are consumed at a slower rate at the beginning of the reaction, when there are not as many molecules of nitrogen dioxide being produced. This is a really dumb explanation, which is not even true. There is no indication about anything of this sort happening. Also, if the reaction is happening, then why, I mean, if the rates are already there, then what does this even mean that, oh, there was, it sounds like someone just making excuses. That beginning of the reaction where there weren't any molecules of, then the reaction wouldn't have happened. That's like that's a very human kind of excuse. And as you guys know, the universe, nature is very different from humans. It doesn't give excuses, ridiculous excuses. Okay. All right. So it definitely has to be graph 1. And then the bulk questions, the videos, everything like that is open on your College Board website. Also, there are 2 very important instruments that you have to remember about. First is the eudiometer, which is used to collect and measure the volume of a gas, okay? So a measuring cylinder, compare this to a measuring cylinder. It cannot measure the volume of a gas, but a eudiometer can collect and measure the volume of a gas. So this is a reaction happening, okay? And we're collecting it over water, and the amount that it's displacing is giving it has the increment, so we would find out how much we collected. And then you have a manometer. A manometer consists of mercury, and it's used to measure pressure. When we were learning about ideal gases, remember how there was a unit of ATM, and then there was also a unit of millimeters mercury, okay? So this is why when we're using this specific device to measure pressure, because it consists of mercury only, this is why we use this specific unit with it. Also, I just went through the concentration spectrophotometer, which tells us that like when something gets darker, it's becoming more concentrated, and as it's getting lighter, it's becoming less concentrated. And then a balance with a high precision can also tell us the mass of a gas produced by deducing final mass from initial mass. I just wrote this over here because I noticed that there were a few questions that expected me to know it. It is common sense, but I want to put it out there. Okay, this is kind of like a longer section, but it pretty much covers up the gist of the rest of the things on this unit. As long as these concepts are clearer to you, you'd be able to understand this entire unit completely. All right, thank you very much.